hardware. So before I get into the talk, I want to give you an idea of who I am. There's actually a quick research profile. So I work in the intersection of algorithms, distributed systems, and data management systems, and combine ideas from these areas or seek to extend them with specialized hardware with the end goal of making data centers more efficient at data processing and management. And in this task, I've had the good fortune to collaborate with a number of very bright people, both from IST Austria and from industrial research labs. And through these collaborations, got the opportunity to explore these topics and their intersections to some depth. So you're looking at this picture and you see specialized hardware. So let me give you a reason why specialized hardware is a relevant platform to research on. So as you might be familiar with, there's two conflicting trends that we are facing. Data volumes are increasing exponentially, and this trend is expected to continue doing so. Whereas the performance of general purpose CPUs is not following the same trend lines. If single core frequencies is an indication of this, you can see that this has been stagnating for almost a decade now. So with this increasing gap between data and compute, we're of course becoming more and more limited in the complexity and the size of the problems that we can solve, and people of course are hard at work trying to narrow this gap. And these different ideas can be grouped, that people are trying out can be grouped into two big paths. And one is roughly speaking about making the computation more parallel. So this can be seen as a way of building larger, more complex distributed systems, but also in designing and making use of CPUs with many more cores. And then the other path is trying to make computation more efficient by replacing the general purpose CPUs that we compute on with something custom tailored to the workload or data types that are of interest. And then even a little bit beyond the horizon, there's research going on replacing the underlying transistor technology that we use today in CPUs with something completely different. In this talk, I will focus on specialization mainly, but also touch on distributed systems a little bit. So for specialization, you might be aware already of some success stories. Google, for instance, has been deploying these specialized processors called TPUs, so tensor processing units, in their data centers, which are used to speed up their machine learning framework. And they are reporting on some representative parts of these operations reporting great results where a fraction of a TPU can outperform 32 GPUs. And of course, there's no magic involved. The reason why the TPUs are so much more efficient is that instead of working on scalar as a basic data type, they use small matrices, which is then much better suited to the machine learning algorithms that they are tackling. And then another example from another area, from genome sequencing. There is a startup called Edico Genome who are replacing parts of the sequencing pipeline with specialized hardware and reporting great speedups, and maybe even more interestingly, 2 orders of magnitude cost improvement on these operations. So that I think this shows that there's already results with specialized hardware, and looking into the future, I think we can even get greater benefits. And to give you a little bit of background, the type of specialized hardware I use for my research is called Field Programmable Gate Array, or FPGA for short. You can think of these as reprogrammable hardware circuits. They are composed of a large number of logic blocks of distributed memory, so small SRAMs on the chip, and DSPs, which are essentially, you can think of them as small arithmetic units for speeding up operations on arithmetics. And what is interesting here is that as opposed to CPU, where somebody has already made the decision of how many cores there are, at what frequency it runs, how large are the caches, in an FPGA you get to choose the architecture yourself. And beyond that, you even get to choose the instructions yourself. You can assemble them in fine-grained pipelines. You can take advantage of the close proximity of logic elements on the chip to build a low overhead communication. And you can assemble the small memory blocks into scratchpad memories or buffers which are co-located with your computation. So just to contrast this again with how we usually think in CPUs, there you have the cache hierarchy has been designed beforehand. The cache sizes are, so to say, cast in stone. The replacement policies are given. So you have to work around that or have to work with that to get your algorithm working. Here you get the freedom of choosing your own or building your own memories. There's of course a trade-off in that all the code that is running on the FPGA will take up some space. So if we choose to implement 3 operations, then we will take up some portion of the FPGA. in the end, this doesn't, at least in the research world, this doesn't limit our ability to explore ideas, because FPGAs are actually nowadays are quite large and come in a spectrum of sizes. So the largest FPGAs have as many transistors as the largest 32-core AMD server CPUs. So there's quite some space to play with. And in the end, I also have to highlight that FPGAs are not in their final form. They are evolving. They are becoming more heterogeneous inside, and they are an excellent research platform for exploring ideas around specialized hardware. In the talk, I will use the word FPGA a lot, but please remember many of these ideas are also applicable to ASICs or other types of reconfigurable hardware, such as coarse-grained reconfigurable arrays. So the ideas themselves are not limited to FPGAs. And the reason for this is that even when we look at how we program FPGAs, the biggest challenge is really the first step, where you look at an algorithm, you look at the problem, and you try and find a way to translate it so that it can take advantage of the parallelism of the device. Then once the initial hurdle has been done, to work with FPGAs, you can either code in hardware definition languages, which are designed, let's say, in a circuit designer's view, so you work with the finished state machines, with the modules, you wire things up. Or you can also work with high-level languages, which are a little bit more productive, so you can use OpenCL or C++, and then use that to get to circuits. Once you have the circuits, these are synthesized. Once you have the code, this is synthesized to a logic gate level representation, so these are the circuits. At this point, you could actually go to an ASIC tool flow and get an actual integrated circuit at the end. But for FPGAs, you go through place and route, so which means that you create a physical representation of the circuit, which can be then downloaded onto the FPGA. So what I will do for the next half hour or so is give you an example of taking an algorithm and, so to say, reimagining it for a specialized hardware scenario. And this example will be regular expression matching with the goal of accelerating parts of text analytics pipelines, both in a database setting or in a distributed data processing setting. And then in the second part of the talk, I will give you an overview of how, once we have these algorithms, how we can plug them into real systems through some examples of systems I work with, and elaborate a little bit on my plans for the future. So are there any questions so far? If not, then I will get into the regular expression matching part. This is probably, you're all familiar with regular expressions. They are used in many, many domains, including text analytics, security verification, computational biology, and so on. And they are generally compute intensive. And what is even, so to say, worse is that their execution time or the cost depends highly on complexity. And I don't mean this in the trivial way where if you have a very long expression, it will take longer to execute, but this can happen in more subtle ways. So to give you an example, we have measured the performance of a state-of-the-art software library, matching a simple expression, looking for a term PO boxes in some address strings. And then we have repeated the same experiment where we've searched for the same two words, but separated by a 0 or more white space characters. And somewhat surprisingly, even though to the human eye, so to say, these two patterns are relatively similar, there's a degradation in performance. And this is undesirable because these kind of fluctuations make resource allocation or query planning, as we call it in the database world, fairly hard because it's hard to predict how long it will take to execute this expression. To give you a little bit of idea of where this problem comes from, I will spend a moment talking about how usually regular expressions are implemented in software. And this is through finished state automaton. And here you see an example of regular expression converted to an NFA, a non-deterministic finished state automaton. So I will not give you a lecture on automated theory and so on. I'm probably not the best qualified person here to do so, but I just want to highlight or remind you what are the trade-offs that we have in software, which then lead to these pure execution properties. So in the case of the non-deterministic finished state automaton, we have a complex size of the automaton, but if, depending on the input, multiple states can be active at the same time. So in this example, if you have consumed the characters A and C of the input, states 1 and 3 will be active. So this means that upon receiving the next character, the software execution will have to look at all the states in sequence and check all their outgoing transitions to figure out which other states will be active in the next cycle. And this leads to this variable execution time. So what people usually do in software is instead convert this into a deterministic form, where by adding states, we remove the non-determinism, so at any point, there's only a single state active at a time. The trade-off here is that by adding these additional states, we can have an explosion in the size of the automaton, which then in software leads to not being able to fit this in the caches anymore, which from there on leads to further degradation of performance. Hardware, on the other hand, is great with NFAs. So there has been a lot of work in running NFAs in hardware, mostly from the networking area. So people use this to do things like spam filters or network intrusion detection with the goal of matching a large number of regular expressions against a stream of data. And the idea of why this works well in hardware is that the circuit itself can be compiled down to, the NFA itself can be compiled down to the circuit, so all parts of it run in parallel. In this example, if we look at our NFA from a previous slide, we can see that on the consumption of the next input character, in the circuit we can actually, for a constant cost, in a clock cycle, we can look at all the outgoing edges, do all the comparisons in parallel, and even take arbitrary number of activations or deactivations, again, in a fixed cost in a per clock cycle. And what this means is that we can actually, regardless of the complexity of the NFA, consume one input character at a time and get an updated state. What we had to do for our work is to extend the state of the art a little bit, because what this mostly focuses on is combining a large number of expressions into a single circuit, and these expressions are known beforehand. And it also, the state of the art makes a lot of optimizations for line rate, so for networking type of scenarios. Whereas what we were interested in is a circuit that gives us a high throughput, so higher throughput than the networking rate, but is able to handle flexibly expressions which we get at runtime, so that we don't know beforehand. In order to build this circuit, we took a step back and constructed the NFAs to its, let's say, basic elements. So we made first-order citizens of characters, transitions, and states, and reconstructed into a pipeline. So what you see here is how the execution works. This still is an NFA. If you squint a little bit, data comes in from the left. It is compared in parallel to all the character matchers, and then depending on the outcomes of these comparisons, we can take transitions between the states. This is pipeline, so while some character is being compared on the left-hand side, transitions can be taken on the right-hand side. This might not look like much, but the magic happens, so to say, behind the scenes. So underneath the character matchers and kind of behind these connections, we have implemented this using some small on-chip memories, where you, by changing the contents of the on-chip memories, you can actually change the characters that are being evaluated, and you can change these connections without actually having to reprogram the FPGA. So in the end, what we get is this dual benefit of, because we use the hardware and because we have a pipeline design, we can pump data through at a constant rate, so at a 1 character per cycle. And because we have this parameterizable design, we can actually switch the expression that we're executing with very low overhead. So this is almost done. The last remaining challenge is related to the fact that all the code that runs in the FPGA takes up space. And if you look at the previous slide, you saw that there is the state graph. If you want to be able to implement any regular expression which fits in that number of states, then we have to make it like a fully connected graph, which will take up quadratic space. And then we try to look at ways in which we can reduce the size of the NFA, or maybe translate it into another representation that will give us some space savings. And in order to do this, we looked at the domain for which we designed this regular expression matcher, which is text analytics, where it turns out that most of the expressions will contain words. And if you look at an NFA matching an expression here, including some person's name, many of the states have a very modest role, so to say. So they are matching just a sequence of characters. They go in a linear type of fashion here. So what happens is, if you extract these sequences and you look at them as tokens, then you can actually collapse the states underneath and come up with a more complex representation where we have a less number of states with more complex transitions in between. But this is good because in hardware we can actually make the circuit that matches on the tokens in linear cost. So we can, the length of the tokens will require only linear cost in circuitry. And as for the state graph, we still require quadratic cost, but now we can reduce the number of states that we support. Okay, so now if we look at the regular expression matcher, we have just created one module. And as I told you, this runs at a fixed rate, so 1 character per cycle, which in our domain translates to 1 byte of the data per cycle. But this is unfortunately, for many use cases, not fast enough. So this is not really scalable, so what we had to do is to explore ways on the chip in which we can use the parallelism to increase the throughput. And to do so, we created a parameterizable circuit, or a templatized design, where we run multiple regular expressions in parallel on different parts of the data. So what you see here is, for instance, four regular expression matches working in parallel. They're all executing the same expression. They're configured together, but then each of them gets a different string, or if in database terminology, each of them will get the string belonging to a different record. What is interesting here is that because of the low overhead communication on the chip, we can actually split the input and then merge the results back with no overhead. So you can really scale this circuit to a high number of parallel units. And that's what this allows us to do, is to come up with a kind of a spectrum of deployment options. So what you see here is we can play with the processing rate on the x-axis, and then we can see how much logic resources the circuit will require. So ALMs are on like a basic building block, this reconfigurable logic element on the FPGA. And as you can see, let's say clocking the FPGA at 200 megahertz, by increasing the number of parallel regular expression matchers, we can linearly increase the aggregate processing rate. And what we pay for it is a linear increase in cost. I have a question.
Definitely not an expert, but is it obvious how you split? I mean, how you can split the input into chunks, so that you get, that you can combine the.
So here, so in our case, and that's what I meant a little bit by the domain, in database or typical or similar workloads, you have the data is naturally split already for you, because the different streams, let's say an address, will belong to different records. So maybe it's an address belonging to a different person. So the data naturally exhibits. So it's not a big blob of. It's not like a very long string, but it's rather a lot of relatively short strings. Let's say in our use case. So then that naturally fits to the. It's a little bit like SIMD processing, let's say, where your instruction is actually not an instruction; it's a whole regular expression. Does it answer your question, or?
Sure. Yes. It cannot match the whole string.
So if your goal is to match a very long string, then that's a different design, and we can talk about it maybe offline. But this is more on the trying to parallelize for many small versions. So then to get back to this graph, what is interesting about hardware is that of course you have multiple knobs that you can turn. So you can also clock your circuit up to a higher frequency. So you can execute this at 400 megahertz, in which case you can get the same throughput, but now using half of the number of parallel matching units. As you can see, the scaling in terms of resources is not fully ideal, because of course the circuit that we put in the FPGA is not only the regular expression matcher engines, but other things like data management or simple transformations that we need in order to get everything aligned. In the end, as a hardware designer, you would at some point have on this graph like a lower, like a limiting line, so to say, which is the maximum frequency at which you can run your circuit. And without getting into too much detail, this has to do with the, let's say, the most complex operation that you're trying to perform in a single clock cycle will determine how you can clock this up. So why is this graph interesting? Because now if you want to deploy this algorithm in a real system, you can look at what rate you expect data to arrive at the FPGA, and then size your circuit just right. So imagine you have a platform where you are going to receive data at 10 gigabytes per second. Then you have the choice of either deploying 40 matchers at 200 megahertz or 20 at 400 megahertz. Deploying more would not really help because it will be over provisioned. Deploying less would lead to constantly or being slower than the data that you can receive. If you would have 6.4 gigabytes per second, then you could deploy 16 or 32 matchers depending on your preference. Now, why would you choose a higher clock rate compared to a lower one? So in our domain, we are always interested in trying to put more functionality on the FPGA. So if you clock this higher, then you can fit more functionality in the remaining space on the FPGA. So if, for instance, you're executing a larger analytics pipeline, then you might be able to offload other parts of it as well to the FPGA. So now we have all the building blocks. The way we get to this kind of abstract view to actual execution is on this slide. So let me elaborate. You see on the bottom left, we start with looking at let's say you look at your problem space. You figure out how many states and characters you need in your circuit to handle the workloads that you're expecting. What is the level of parallelism that you want to have in the circuit to match the data rate, and then combine this with the templatized circuit that we came up with to produce an FPGA image. And then this is loaded onto the FPGA. And at runtime, as you can see in the blue kind of workflow, through software, you transform first the reg expressions to an NFA, and then extract the sequences, create a compact representation, generate these small configuration bit vectors, which are at that runtime just loaded onto this circuit. So you don't need to reprogram the FPGA every time. And the question is whether this pays off. So let me show you some numbers. Here I chose 6 expressions which are representative for database workloads and some network intrusion detection scenarios. And we are running this on an experimental platform which has an FPGA close to an Intel Xeon CPU. In this specific platform, the FPGA is limited at 5 gigabytes per second bandwidth to the memory. So the circuit itself could go faster, but we're bound by the memory bandwidth. We're comparing against a fairly standard server-grade CPU, and what we're measuring is how many cores of the CPU you would need using the 2 state-of-the-art software libraries to match the throughput of the hardware. And as you can see, so as we go with the different patterns, you can do this either with, let's say, 2 to 4 cores, or maybe you need the whole socket. But in the end, you will need many cores, especially for the more complex expressions. And what's even more interesting here is that in hardware you get the same throughput for all of the expressions. So regardless of the complexity, you get the same behavior. And finally, as I told you, because there's space on the FPGA, you can actually combine this matching with other functionality as well. One thing I unfortunately don't have the time to go into detail. But one thing that can happen is that you provision the FPGA with some size, some number of states, and some number of characters, and your expression doesn't fit on the FPGA. So we've explored this case and come up with a solution where you can split the expression between the FPGA and the CPU. And if you do this splitting in a smart way, you can actually make sure that in every case it will be worth pre-processing on the FPGA and then post-processing in software. Okay. So before I wrap this part up, I just want to say a few words about related work, because there's truly been really a lot of work on the reg expression matching in FPGAs and in software in integrated circuits. And the work goes back all the way to the 70s in trying to come up with more efficient representations, in trying to compile finished state machines directly to hardware. And in the FPGA world, most of the effort recently has gone into finding ways of combining a large number of expressions into a single circuit that can be loaded onto the FPGA. In software, there's also been a lot of work in speeding reg expression matching up, and most of this work these days focuses on using the SIMD, so the wide vector units inside CPUs and GPUs more efficiently. And then even in hardware, I need to say this, there's work which looks at how you can come up with flexible circuits. However, this related work focuses usually either on replacing only the characters or changing the transitions but not the whole expression as we do in our work. So I will pause for a moment. If there's any questions to this, I'm happy to take them now.
I just have a small question related to this, essentially throughput not being dependent on the complexity. I mean, somehow this seems unnatural because you have very long expressions.
Exactly. So that's what so that's a good point. So throughput is not dependent on complexity as long as you fit in the confines on the FPGA. So that's why I mentioned a little bit the hybrid execution. You can still do very interesting things even if you fit the only part of the reg expression. The trick there is which part you actually want to put in the FPGA. Okay. So I talked about reg expressions with the goal of giving you a feeling of how we go around our work of taking an algorithm or taking a problem and trying to understand how specialized hardware can accelerate this. But of course, reg expressions are not the only thing that we've done. So in the group, throughout the years, we built up a library of operators or library of things that we can accelerate, and I probably worked on at least one out of each of these things in the categories. But the point here is to say there's really opportunity to accelerate. So if you have an algorithm which is compute intensive and you want to talk to me, I'm happy to see if specialized hardware could be a solution there. What is also important is that throughout this exploration we understand which are the algorithms which are not necessarily well suited to specialized hardware. So we don't try to see if we have a hammer, we don't try to see everything as a nail. And in some cases even try to understand when we need to come up with completely new algorithms for this hardware. But in the end, all of this work is done not for itself. It's not for it doesn't exist in a void. The goal is to build real systems. So my goal has been to do this work in order to plug it into something larger, in order to speed up a larger system around it. And for the remaining of the talk, I will give you essentially an example of using FPGAs in different parts of the architecture because they can be deployed in different ways. And I will also give you an idea of the ecosystem, let's say, around it, and how this is expected to change or remain in the future. So there are multiple ways you can deploy FPGAs, and maybe the most, or specialized hardware, the most obvious one that comes to mind is an accelerator. So here the specialized hardware sits on the side of a regular machine, and it offloads some operations to hardware. But there's also other ways. So for instance, bumping the wire is when you put the specialized hardware in a data path, so between two machines, for instance, in the network, or between CPU and memory, or a disk and CPU, and you try to filter or transform data in a way that benefits the application running on top. And then finally, you can even think of building systems only with specialized hardware. So in my dissertation work, actually I've looked at how you can replace a whole layer of server machines with specialized hardware nodes which give you the same service, maybe at the lower latency and higher throughput, while being a smaller footprint specialized device. So what I will do for the remaining, I will go a little bit, use this outline to present you some systems that I worked on to give you a feeling of how these things can be deployed. So for the accelerator use case, one of the most interesting platforms is the Intel Xeon plus FPGA, and now it's called Research Prototype. So the first generation device that I showed you some evaluation numbers on was a machine where one socket contained an FPGA and one socket contains a CPU, and the FPGA has access to the CPU's memory in a cache coherent manner. So this is not that much different from how PCI Express attached accelerators work. The only exception is that in order for the FPGA to get to the data of the CPU, there is really no need for data copy. It can work almost as let's say, another thread on the data. So this was already a good start, but then in a matter of years, so last year they already released the second generation version of this, where the FPGA is on the same package as the CPU, so they are sitting in the same socket. So now you're not replacing a CPU anymore with the FPGA, but rather have this tight integrated with the CPU. And if what Intel is telling us is true, then very soon you will have this small FPGA deployed with your server-grade CPU. So whereas a few years back when I started my PhD, the discussion was, well, do you really want to replace a CPU with an FPGA? Do you have enough proof that that will accelerate your workload more than using another CPU? This question has turned around completely, and now the question is, well, you have an FPGA in your CPU. How are you going to use it? And one way we think is interesting and shows some promise is by extending what analytical databases can do today. And this is a large project going on in our group called DoppioDB, so it involves almost everyone working on FPGAs in the systems group. And the goal is to look at analytical relational databases, how are they designed today, and extend their capabilities using specialized hardware. The really interesting part here is that we're doing also a lot of engineering work to enable things like including hardware and software operators inside the same queries, even maybe splitting a single operator across software and hardware. And as an example, when we looked at text analytics queries and even building more complex things on top, it turns out that regex special matching is a big pain point in databases, so that we, for instance, use the regex special matching circuit I showed before as part of DoppioDB to offload these operations. But then, even if you don't believe me that that accelerators are coming, there's other examples. So Amazon, Baidu, and Huawei are all renting out machines with PCI Express attached FPGAs by the hour, and Microsoft has been deploying them in production for years now. So what happens is they actually have an FPGA now deployed with every server in their Azure cloud to offload networking functionality, but thanks to the positioning and the design of this device, it can be used for other tasks as well. So it can be used for acceleration or either in-network processing. So maybe you have seen the Brainwave article that Microsoft has published a while ago, where they show how they accelerate machine learning with FPGAs. So that is done on the Catapult platform. Speaking of on-the-wire or bump-on-the-wire processing, there was this project in our group when I started my PhD called IBEX, where we looked at how you can use an FPGA to offload processing into a storage device. So the idea was that if you have a database engine which works on analytical data sitting on a flash drive, on a solid-state drive, the bottleneck is often moving the data from the solid-state drive to the CPU. And then what we can do is, by putting a small specialized device between the drive and the CPU, we can already pre-filter based on some expressions. I worked on the aggregation part, so we can start computing these group by aggregates, and even provide background statistics on the data that is being loaded to the database, that on the execution layers on top, will help with taking the right decisions. So this was done in 2014, and this was this was published in 2014, what was done before. And data rates were more modest, let's say, at that time for SSDs. This was running at on the order of 500 megabytes per second. And also their IOPS were not so high. But if you fast forward to today, there's actually now PCI Express attached flash devices available, which have very high throughput, very good random access properties, and they have small near data processing elements which can be used to offload this processing. So this is an example from Samsung, and many of the ideas that we did in IBEX, even though we did it on an FPGA, are immediately applicable to this near data processing element in the Samsung Smart SSDs. And then based on this, I get to the work that I've done for my dissertation, which is Caribou. So Caribou is a smart storage for distributed applications, and in some way it is the reincarnation of IBEX for the cloud, which has been designed with the same goal of filtering data or processing of data close to source, but taking into account the realities of large distributed applications these days. And you are probably familiar with this framework. So MapReduce and Spark and even distributed databases work the same way. You have a logical and physical separation between nodes which do data storage, so here you see on the bottom, and the nodes which do computation on top. And usually in these systems, This separation has allowed them to scale to a large number of machines. It allowed the two layers to be provisioned differently, but it also introduces data movement bottlenecks, because now you have to move data across these machines every time you execute queries. So what people are exploring in software is pushing down computation again to the storage to alleviate these bottlenecks. And what I've done in Caribou is to provide these services in a small footprint hardware device, which replaces, so a server is replaced by an FPGA. And we provide all the standard stuff here, so we have implemented interfaces which are essentially a drop-in replacement for software key value store. So here the key value means that the lookup or the access interface to the storage is on a tuple basis. We provide replication for fault tolerance, which actually was probably the most difficult thing I've ever done in FPGAs, is to build a distributed consensus algorithm all in hardware. I'm happy to talk about this offline if this sounds interesting to anyone. And then also push down processing into this layer by using the similar design ideas that I was talking about with the regular expression mentioned, where you try to massage these algorithms in a way that they provide you a fixed bandwidth regardless of the complexity. And each node is really just an FPGA, as you can see, with some amount of memory, with extensions to attach SATA drives or emerging non-volatile memory technologies, and then network connections, which then I use to talk to the clients. So then the reason I built Caribou is not to just have a one-off effort and be done, but really to have it as a platform for further exploration. So we have open sourced it and made the design modular, so that if the problem of data management is now solved, we can use the key value interface, we can use the replication, and this enables us to put different types of processing on top. So for instance, in our group, we are exploring with Tse how some parts of machine learning pipelines for astronomy data can, for instance, be pushed into the storage, because there is a lot of data that all of the people working on top share, so there's only one universe. And then we have actually found very nice subparts of machine learning operators that can be pushed out into the FPGA. And then beyond that, this is another thing I'm very interested in doing, is taking the replication module inside Caribou is built on top of an atomic broadcast protocol, which solves the distributed consensus problem, and this can be used in the future as part of smart NICs, so these are network interface cards with FPGAs, to offload parts of distributed consensus operations. So to wrap up, I think if we look ahead, it's clear that data centers are changing. We are going to get more heterogeneous systems, which means that we will have to continue reimagining our algorithms. We will have to continue rethinking them or adapting them to this heterogeneous hardware. The systems that we have today will likely have to adapt as well and be changed in order to take advantage of this heterogeneity. And then if we look at parallelism, this is also not going away. If anything, distributed systems will be larger and more complex. And I think there's a lot of opportunity to, well, not even opportunity, but really the need to introduce smartness at different layers of the architecture to make sure that data is only moved when and where necessary. And as I pitched during the previous slide, I think even with the problem of consensus or coordination in large distributed systems, we can use some help of specialized hardware. In the end, what I would really like to be working on in the future is kind of a collaborative design of the next generation of data processing systems, together with other scientists from other areas and people who work on algorithms, software, architecture, and try together to kind of come up with a holistic design for these systems. With this, I would like to finish and open for questions.